Hello, my name is Cesar Silva and I'm a professor of mathematics at Williams College. The title of my presentation is there a power of 6 that starts with a 9? We will see that this question will lead us to explore ideas in real analysis and dynamics. Background. This is mainly addressed to students taking a real analysis course. That is, you have already taken calculus, perhaps another course, and have started real analysis, and you may have already done 3 or 4 weeks. What are the basic ideas we will need? We will need the notion of a function, what rational numbers and irrational numbers are, and basic ideas about sequences. So we start with an outline of our presentation. First, we will talk about what it means for a number to start with a 9. Then we will set up an equation that describes precisely when 6 to the n starts with a 9. To explore that and answer that question, we will introduce a transformation, that is a map on the unit interval, and we will introduce the idea of orbits of a transformation. And then we will mention Kroneker's theorem and how Kroneker's theorem helps us answer that question. This is part 1. There are 3 parts to this presentation. Now you may ask, why about 6? The only role of 6 here is that the logarithm of 6 base 10 is an irrational number. So we will see that once we end the presentation, we will see we could have used 2 or 5, any other number whose log is irrational. And this is something we assume that you know how to prove that the logarithm of 6 base 10 is irrational. So let's start with a question first. Does a power of 6 start with a 9? What do we mean by a number starting with a 9? For example, 3 cubed, that the third power of 6, starts with a 2. It also starts with a 21. We might look at the first digit, or sometimes we may look at the first 6 digits or any fixed number of digits. Once we have answered that question, we may ask also, what about infinitely many powers? Are there infinitely many powers of 6 that start with a 9? And then we may also want to know, maybe there's a power of 6 that starts with your 7-digit phone number. Let's look at the first 18 powers of 6. If we look here, 6 to the first, 6. Let's look at the first digits. So what do we see? On the first digits we see 3, 2, 1, 7, 4, 2, 1, 1, 6, then 3, 2, 1, there's a 7, 4, 2, 1, 1. First 18 powers. So we're looking, that's a table where we have looked at the first digits of the first 18 powers of 6. Now, let's look at the question then, when 6 to the n starts with a 9. Okay, so if 6 to the n starts with a 9, it has to be between 9 to the k, greater than or equal, and less than 10 to the k, for some k. So for example, take a number, this is not necessarily power 6, it's not a power 6. So take a number that starts with a 9, like 921. It is between 9 times some power of 10 and 10 times some other power of 10. Less than or equal on the left, strictly less on the right. And in this case, it would be k equal 2. So let's go back. What does it mean? Let's look at the first equation now. And what we do is take logarithms base 10. So if you take logs of the first equation, or log of a product of sum, so we get that log 9 plus k less than or equal than n log 6 less than 10 log 10 plus k for some k. Now we can rewrite this as saying that n log 6 is in the translated interval log 9 log 10, translated by some integer k. Okay? So that's what it means for 6 to the n to start with a 9. N log 6 is in log 9 log 10 plus k for some k. So let's continue that and analyzing that in more detail. We will introduce this idea of modulo 1 to take care of this plus k. So we will see that a translated interval, n log 6 is since translation of the interval, so that means that n log 6 modulo 1 is in the interval log 9, log 10. What is a number modulo 1? You subtract the largest integer less than or equal to that number. So you look at the number just in the unit interval 0, 1. So for example, 3.14 mod 1 is 0, 1, 4. 1 mod 1 would be 0. Okay. So when we take a number and we do mod 1, we just get the fractional part in 0, 1. Now let's look at some of the log 6s. So log 6 is 0.77. 2 log 6 is 1.55, but mod 1 would be 0.55. 3 log 6 mod 1 is 0.33. Okay? So what we are interested in is looking at these numbers n log 6 mod 1, and we will be getting some numbers in the unit interval 0, 1, starting with 0.7, approximate 0.7, 0.5, 0.3, etc. So now, to study this number n log 6 mod 1, the sequence really, in more detail, we introduce a transformation. A transformation is a function from a set to itself so that we can iterate it. So that means we can apply the transformation again to the result. You start with x, you apply t to x, you get t of x, and then since t of x is again in your set where t is defined, you can apply t to that again. Okay, so the transformation that we introduce is defined by t of x equals x plus log 6 mod 1. So it's a transformation defined in the unit interval. Okay. The way we will think about it is, first you think about a rotation. You start with x and you add log 6. But since we identify 0 with 1, as you get closer and closer to 1, past 1, it turns into a rotation. So we will see that we can view this as a rotation. First, let's look at more detail at what we call the iterates of t. So that's applying t several times. So t of x is x plus log 6 mod 1. What is its second iterate? Second iterate means you apply t 2 times. So first, t square of x, we denote that the second iterate. T square of x is t of x. T of x is x plus log 6. You apply t to that again and you get x plus log 6 plus log 6. So t square of x is x plus 2 log 6. Similarly, t cube of x, you apply 3 times, it will be x plus 3 log 6. And if we continue, the nth iterate of t to the n of x, will be x plus n log 6. And now we come back to that n log 6 that we saw before. That was crucial in understanding whether a power of 6, in this particular case, 6 to the n, starts with a 9. Okay. So we have seen this transformation now. We have defined a transformation on the unit interval, and we have looked at its iterates, and we see that the nth iterate of this transformation at x is x plus n log 6, mod 1. In all of these cases, we do that mod 1. So now let's look at more detail at what we call the orbits of a point under the transformation. If you have a point x, the orbits of x consist of the sequence that is obtained by iteratively applying t to various points in the sequence. So you start with x, you apply t to that, get t of x, you apply t again, you get t squared, t cubed, you get an infinite sequence. So that we call the orbit, or sometimes people may call that the positive orbit, because you are looking at the forward orbit. Now let's concentrate in the orbit of 0. We look at the orbit of 0. X now is 0. So the first point is 0. Now t of x is log 6 because it's 0 plus log 6. T squared is 0 plus 2 log 6. T cubed is 0 plus 3 log 6. So here we see the sequence whose nth term is n log 6 is the orbit of 0. Okay. Now let's recall the original question. The original question was, is there a power of 6 that starts with a 9? Or in other words, does 6 to the n start with a 9? And we saw that 6 to the n started with a 9 has to do with n log 6. Let us n log 6 being in some interval. N log 6 mod 1 is in the interval log 9 log 10. So we can rephrase the question of 6 starting 6 to the n here, starting with a 9, there it says 6, you should 6 to the n starting with a 9, if and only if t to the nth of 0 is in the interval log 9 log 10. Log 10 is 1, so sometimes we write it as 1, but we will typically keep the log 10 just to remind us where it came from. So what we have found here is that 6 to the n starts with a 9 if and only if t to the n of 0 is in the interval log 9 log 10. Okay? So we have rephrased the question about a power of 6 to start with a 9 to a question about the orbit of 0 under this transformation, and in particular whether the orbit of 0 under this transformation is in this specific interval log 9 log 10. Now let's look at an example here. The orbits under some other rotation. In this particular case, the figure illustrates a transformation which is x plus alpha in the particular case where alpha is log 2. Okay? Just to get an idea of the dynamics. And we're going to look at the orbit of 0 for this transformation. So in this log 2 is about 0.3. It's approximately 0.3. So we start, since we identify 0 with 1, we think of this as a rotation. And we start at 0. The first point in the orbit, the next point in the orbit is alpha, so we rotate to alpha. The next point in the orbit is 2 alpha, and then we go to 3 alpha, etc. And then, as you could see there, and it's rotating, it's coming back, and things are getting closer to each other. For alpha is to the left of alpha. And we will see in part 2 of the presentation that this orbit, when alpha is an irrational number, consists of points that are all distinct. This will be covered in part 2. So what we have done here is get an idea what of the dynamics of a rotation by alpha. Okay, rotation by alpha is the transformation t of x equals x plus alpha. And in this particular case, we're looking at the dynamics when alpha is log 2. Now, one may also consider, instead of taking alpha irrational like in the case of log 6 or log 2, you may rotate by a rational number. So for example, what happens if you rotate by a half? You start at 0, you go to a half, and then you go back again. If you add a half plus a half is 1, mod 1 is 0. You go back. We will see that if you rotate by a half, in this case, every point comes back under 2 iterations, and we say that this transformation is periodic and every point has period 2. For every x, the second iterate of x is x. Okay. So the dynamics of rational rotations is very different from the dynamics of irrational rotations. We have seen that in the case of irrational rotations, we will see in part 2, the orbits are infinite. They never come back to themselves. So now we introduce Kroneker's theorem, which will answer the question, does 6 to the n start with a 9? Suppose now that alpha is an irrational number. So Kroneker's theorem says take alpha irrational and define a transformation t to be t of x equals x plus alpha mod 1, transformation defined in the unit interval. Kroneker's theorem says that for every x, if you look at this orbit of x, that's a sequence, that sequence will be dense. Now the notion of denseness is an important notion that is covered in real analysis that you may not have seen yet, and that's all right because we're going to cover what it means here. Dense means that it intersects every interval of positive length. A dense sequence is a sequence that intersects every interval of positive length. one of the first examples of a dense sequence that you see in real analysis is the sequence of rational numbers, which are dense in the real numbers. Kroneker's theorem says that for every x, if you look at the orbit of x, the positive orbit of x, it will be dense in the unit interval. So that means given any interval I of positive length, there will be some n so that t to the n of x is in I. Okay, it will be an element of I. We will see that from this fact it follows that there exist infinitely many n's, and that will be explained in part 2. We will cover that in part 2. So this is Kroneker's theorem. Now let's review Kroneker's theorem in the context of our transformation. We are interested, remember, in the orbit of 0 because we know that t to the n of 0 is n log 6. And we want to know whether n log 6 is in the interval log 9 log 10. But we already said that n log 6 is t to the n of 0. So we want to know whether there's an n so that t to the n of 0 is in log 9 log 10. But Kroneker's theorem just told us that for every x, in particular for x equals 0, the orbit of x will be dense, so there it will intersect every interval. So Kroneker's theorem says that there will be such an n. There will be an n so that t to the n of 0 is in log 9 log 10. In part 2, we will see a proof of Kroneker's theorem. But now we just saw that Kroneker's theorem gives us the answer that indeed, yes, there is an n that starts with an I. Now, if we had done this by computation, it would have taken us a long time. Turns out that the first n, so that 6 to the n started with 9, is 176. So that we see a first digit. So this ends the first part of this presentation. Thank you.